Let's understand how to interpret machine learning models in this one. We have seen a couple of popular use cases, that is linear regression and decision trees. We have seen this earlier. Whenever you are trying to predict a numerical quantity, we call it as a regression problem. Whereas whenever you are trying to predict a categorical variable, you are going to be calling it as a classification problem. Now we are going to see first linear regressor. A machine learning model that performs a regression task is called a regressor. So what we are going to first see is a linear regressor and how to interpret it. Let's understand this with the help of the housing price prediction problem. In housing price prediction, we want to predict the price of a given house given various inputs. Now, in this particular case, we have these inputs: the area of the house, bathrooms, stories, air conditioning, parking, and pref area. These are the different inputs that we are giving to the machine learning model. And how this model itself is getting created is we are building a linear regression model that predicts the housing price as a function of all these inputs, that is area, bathrooms, stories, air conditioning, parking, pref area. So this is how we typically represent objective of this particular problem itself, right? Now, on training a linear regression model from this, you get an output that looks something like this. The output is basically the coefficients of each of these input terms. The coefficients of A, B, that is area, bathroom, and so on. All these coefficients is basically the output of your linear regression. Now, how to read this? By the way, this is trained based on scikit-learn package, which is based out of the Python programming language. If you do this with any other language also, you will definitely have the coefficients of the respective terms, which is the primary output of this particular, of any linear regression model, not just this one, any linear regression model, you will get the coefficients at the output. Now let's understand how to read this. Say you are having a house. For that house, you want to know what is the price, and you know the values of these parameters. Say I'm going to call the value of area as A. The housing price would be A into the coefficient of the respective parameter. In this case, 267.3139. This is for area. Likewise, we do for all the other terms that is present here. So number of bathrooms multiplied by this term, 1.141 e power 6, plus stories, 4.65 e5, and so on, right? All the different terms you have, plus you also have the constant term. Right? The constant term should ideally come in the beginning itself. So 3.743 e power 5. So this is how you calculate the price of a given house if you are given the values of the respective parameters that you have in your linear regression model. So how that actually translates as, let's suppose you have the area as 7420, number of bathrooms is 2, stories is 3, air conditioning is 1, parking 2, pref area 1. So these are the input values. Can you come up with what is going to be the price of the housing price given these values? How would you calculate it? Just put it in the formula that we just saw. So housing price is nothing but this value, I'm going to call it constant, plus 7420 multiplied by this value, area, coefficient of area perhaps, plus number of bathrooms 2.0 multiplied by this term, and so on. For all the other terms, we add this. This output is going to be the price of the house. So this is how a typical linear regression model internally stores this information to map your inputs to the price of a given house. So this is how you make the predictions. Now, what else can you take away from this? Another information this also tells you is, say if you increase the area of the house by say 1 unit, you increase the area by 1 unit. How much is the price of the house going to change? How much is the house price going to increase or decrease? How do we know that? It can be known directly from the coefficient that you have here. So by increasing the area by 1 unit, since you are going to be multiplying this value against this value, if you increase area by just 1 unit, so say it becomes 7421 instead. By doing this change, the house price is going to increase by this much amount. That is $267.31. Now, what would happen if you increased air conditioning from just 1 2.0, what would happen to the price? The price would increase by this much factor, that is 8.684 into 10 power 5. By this much factor, it is going to increase on increasing air conditioning from 1 to 2. Now, what does this tell you? If you increase the area of the house by 1 unit, it is just changing this much. But by adding one air conditioner, it is going to increase the price by so much. This does not sound right, isn't it? So, just by looking at the values of these coefficients, you can make sense of the model that you are being shown is a credible model or not. So in this case, it is not really a credible model that is going to give you an accurate prediction of HP. It is not a realistic model as such. This can happen if you did something incredibly wrong or if simply your data is corrupted or it does not really represent air conditioning data itself. So these are some other things you need to be careful and not just take things at their face value.